Welcome to Lecture 8, Newton's Discovery, a title which has a double meaning because we shall talk both about what Newton discovered and we shall talk about the discovery by Europe of Newton's accomplishment. Note well, by the way, the homage paid by the 20th century to the 17th. If you think of our cutting-edge technology, computers, we have just lectured on Pascal, who has given us a 20th century name for a computer language, and now Newton, who's Apple, and indeed the Newton itself are hallmarks of 20th century technology. The context of the emergence of Isaac Newton upon European consciousness is not uninteresting. Throughout Europe, by the mid-17th century, young men, for women are not being educated formally in the 17th century, young men are drawn to societies of mathematically and mechanistically oriented empirical natural philosophy, what we in the 20th century would term science. And these societies exist almost always wholly apart from the universities of Europe. All throughout the 17th century and well into the 18th century, the European universities continue to teach in Latin the curriculum of the early 17th century. It is as if Copernicus and Galileo, as if the great figures in anatomy and physiology of the early modern world never had written. There were received authorities, they continue to be taught. The European universities are dominated by Aristotelian physics, with its qualitative and its teleological concerns about motion and about the order of the physical world, such that those who are drawn to the new ways of looking at nature and reality and knowledge and the acquisition of knowledge create societies and institutions apart from academic life, much in the same way that in the 20th century in certain fields of the social sciences one sees think tanks, right, left, and center, doing a different kind of social research or policy research from what is being done at the universities in the 17th century far more dramatically. The dominance of Aristotelianism, scholasticism at the universities leads to these extra-university institutions that become the scientific societies. In England, from the 1640s on and throughout the English Civil War, which pales in comparison in terms of its historical influence to what emerges from the work of the British scientific societies, there are meetings of students, tutors, professors from London, Oxford, and Cambridge that are meeting informally outside of official structures. They share a common interest in non-Aristotelian, indeed anti-Aristotelian natural philosophy, which they call usually experimental philosophy or the new philosophy. They are a generation excited both by Francis Bacon and by the progress of the mechanistic and quantitative sciences. This poses an interesting problem for historians of science who have spent an extraordinary amount of quite valuable time demonstrating why Bacon is not at the heart of the scientific revolution, because Bacon does not look to quantitative, to mathematized views of nature. If you think back to our lecture on Francis Bacon, Bacon was deeply concerned about the mind's tendency to fly toward order, not to move gradually from generalization to generalization. And many historians of science and philosophers of science want to say that Bacon's vision in the New Organon had very little to do with the mathematized quantitative science that emerges later in the 17th century. The problem is that almost all of those quantitative scientists called themselves Baconian. They read Bacon. They were excited and inspired by Bacon. They believed that what they were doing was observing nature, framing generalizations as Bacon urged, testing those, and reaching higher and higher levels of generalizations. And whatever 20th century historians of science or philosophers of science want to say, in the lived historical reality of the 17th century, the devotees of the new philosophy saw themselves as Baconian and saw themselves as drawn to quantitative, ever more mechanistic explanations of nature, and saw absolutely no conflict between those two inspirations. By 1660, the English group is meeting weekly for the pursuit of what it now termed, and it's a wonderful 17th century phrase, quote, physico-mathematico-experimental reasoning, end quote. Physico-mathematico-experimental reasoning. They wisely choose as their president a member of the Royal Council in the newly restored Stuart monarchy, which opens up a flood of patronage to the new scientific society. And in 1662, they are chartered by King Charles II as the Royal Society with approximately 130 members. The attitude of the members of the Royal Society is that which Galileo had expressed so well in his debates with the Aristotelians. Don't look in books to understand nature. Don't look at the written word to understand nature. Observe nature. Frame your hypotheses from observations of nature, and test those hypotheses in nature itself. The activities of the Royal Society are above all two. They engage in, on the one hand, experiments and observations, and two, fulfilling Bacon's vision that the new learning must be dynamic, cooperative, never static, never the work of one person, one genius in reports. They communicate their work, and they communicate their work not only amongst themselves, but to the broader public and to similar societies devoted to the new philosophy that are emerging all across the European continent. In 1664, the Royal Society divides into committees that express the interests of members and that organize the work of the Royal Society. They divide into 8 committees. The first is mechanical, the study of matter in motion, what we would think of as physics. The second, astronomical and optical. The third, anatomical. The fourth, chemical. The fifth, agricultural, fulfilling the vision of Bacon and indeed Hobbes and indeed Descartes, that knowledge can be applied to the immediate needs of the human condition, the most fundamental issue of want and scarcity on the one hand, or the application of knowledge and the production of bounty on the other. The sixth committee is on the history of trade, and much of it is also concerned with navigation. The seventh committee, and I will give you its name because it reveals so much of that sense of discovery that is so central to the 17th century. Think back on Kepler's sense. Had not God himself waited 6,000 years for someone to gaze upon his work with understanding? That sense that with proper method, one was looking for the first time with understanding on the world in which one found oneself. The seventh committee of the Royal Society was a committee, quote, to record phenomena of nature unrecorded or hitherto unobserved. And the eighth committee was a committee of correspondence. The influence of Bacon upon the Royal Society scarcely can be overestimated. By 1670, Bacon's utopia, the New Atlantis, with its portrait of the House of Solomon, the natural philosophers, at the center of providing essential knowledge and understanding to a society, had gone through 10 editions. And for the Royal Society, it is a work that defines so much of their self-image. On the first publication of the transactions of the Royal Society, reporting their experiments and observations to the world, the frontispiece of the work gave us a portrait of the King of England surrounded by two figures, the President of the Royal Society and Francis Bacon, who is labeled, quote, the restorer of the arts. Arts means applied human knowledge. That's why we have faculties of arts and sciences. We use the medieval and early modern meanings. Science was systematic understanding, the organization of knowledge. The arts was the application of human knowledge to the world in which we found ourselves. The English public eagerly awaits publications of the transactions of the Royal Society, which are a wise combination from the standpoint of patronage, expanding interest, and expanding membership of scientists and what were known as virtuosi, so that next to each other you would find articles that were path-breaking in foundational sciences emerging in the 17th century. Optics, physics, mathematics. Next to it, a recipe for mulberry wine by a country squire, a gentleman, who now felt himself a part of this new community of learning and applied knowledge. There were those who satirized the reports of the transactions, and in that combination of works on physics, works on navigation, many of them central to the history of Western science, observations and measurements of height, barometric pressure. There are scores and scores of people publishing simple measurements, improving our knowledge of the natural order, designs for pumps, for clearing mines of water that are applying the frontiers of our knowledge of barometrics and pneumatics and hydrology to human productivity, and indeed, recipes for cider and advice on animal husbandry. The publication in the Transactions of a work by a largely unknown man, Isaac Newton, his Optics, was both a major event in the history of Western science. It gave us our modern theory of light, and for almost all readers, their first introduction to the man who would become Sir Isaac Newton, the most celebrated natural scientist of his, or perhaps of any age. Newton was the son of a Lincolnshire farmer born in 1642. And from his early education, it would appear that his father had destined him to be a well-educated farmer. But in 1661, Newton entered Cambridge University. Cambridge was dominated by the Aristotelians, but Newton entered Trinity College of Cambridge University, where alone the Cartesians were strong and influential. And the young Newton is introduced to Descartes' analytic geometry, and to higher mathematics in general. Newton, although he will overturn, as we shall see, the physics of the Cartesians, had early ties and debts to Descartes' system. And he was taught by a man named Isaac Barrow, who was the most distinguished mathematician in Britain and who held the most prestigious chair in mathematics. In 1665, Newton received his Bachelor of Arts degree, but then Cambridge emptied because of the Great Plague of 1665, when people would leave, who could afford to, would leave population centers and get themselves to the relative safety of the countryside. And Newton spent 18 months thinking in Woolsthorpe, his family's country home. What was Newton thinking about for those 18 months? Well, he was thinking about, among other things, the motion of the moon and the problem of a swinging globe, as shown by the great mechanistic scientist Christian Huygens. If you think about the problem of a swinging globe, you will understand what underlies so much of the drama of what Newton is doing. You look at the world, you look at the heavens, you look at whirlpools and circular motion, inertial circular motion appears to be a natural motion. The heavens, the planets, the moon remain in circular orbit around the Earth. Only Kepler had hypothesized elliptical orbits. He could not prove that. Huygens focuses upon the problem of a swinging globe. You get a globe swinging, and then you let go of it. And what happens? It does not persist in circular motion. It flies off in linear motion. While thinking about this, an apple indeed did fall. That part of the Newton story is absolutely true. And Newton begins to think about what would be a force that would draw the apple to the earth, and assuming inertial linear motion, that when released from the force of that string or chain, when one swings the globe, the object achieves linear rather than continuing in circular motion, what would be the force that not only would draw the apple to the earth, but would preserve the same force, the moon in orbit? The easiest way to conceptualize this, a force that would serve as an unseen string on the swinging globes of the heavens. Many people were thinking about this problem, and Newton arrived at a calculation that no one else had been able to derive from the problem or from the data. That the pull of the earth diminished according to the square of the distance of any object from the center of the earth. But Newton did not have his college books with him, and the figure that he used for the circumference of the earth to calculate distance from the center was slightly off. And as he wrote, he, quote, pretty nearly, end quote, proved his calculation. In fact, he had discovered the law of gravity, but his proof slightly off, he set it aside and mentioned it to no one. Finding it difficult to work with multivariables of space, motion, and time with only Descartes' analytic geometry, Newton developed the integral calculus. Leibniz was doing the same thing simultaneously on the continent. Thinking about motion and about Galileo's law of falling bodies, he posited the three laws of dynamics of motion that dominate classical physics, that lay the foundation of all subsequent physics. How do Galileo's abstract mass and force behave? Newton posits the law of inertia. A body in motion continues in a straight line until acted upon, unless acted upon by another force. A body at rest remains at rest unless acted upon by another force. He posits that force as a ratio. Velocity equals time times acceleration. And he posits that for every action there is an equal and opposite reaction, a law of motion that is true at all times except when I play billiards. Newton, during those same 18 months, thought out the nature of numerical series, and with the prism discovered the composition, the nature of light. In short, in the 18 months that followed his receipt of a Bachelor of Arts degree, and at the age at 23 to 24, which is very late in those days, but there had been a civil war in England, Isaac Newton had formulated the law of gravity, formulated the essential laws of mechanics that would govern Western physics, created the infinitesimal calculus, laid the foundation of modern optics with his experimental discovery of the composition of light, and done major work on numerical series. Now, typical of Newton, who often forgot to eat, he communicated not a word of all of this to anyone. When later in the 1660s he showed his work on mathematics to Isaac Barrow, Barrow did something that has never happened before and will never happen after in the history of the academic world. Barrow immediately resigned his chair in mathematics and insisted that it be given to Newton. If you're one of my students, don't even think about it. But no one knew of Newton's work on gravity or on the laws of motion. In 1684, some 20 years later, there is a meeting in a coffee house in London of three of the greatest minds in England. Edmund Halley, the celebrated astronomer, Christopher Wren, the great architect, and Robert Hooke, astronomer, mathematician, and the first great discoverer and theoretician of the mechanical laws of the elasticity of mass. At that coffee house, the three men are discussing the problem of Huygens' pendulum and the swinging globe and the moon and its orbit. Newton had seen the connection 20 years before. Hooke proposes the inverse square law. Christopher Wren thinks about that and wagers that it could not be proven. Halley and Hooke, who are brilliant mathematicians, set to do that and are unable to provide a mathematical proof that the inverse square law would account for the heavenly motions, the orbit of the moon, or in any manner be consistent with what we knew about laws of motion in general. Frustrated about their inability to get a mathematical proof of the inverse square law, they send Edmund Halley to Cambridge to solicit the views of someone who is simply known as being one of the finest mathematical minds in England, Isaac Newton at Cambridge. And Halley, when he is let into the chambers of the great mathematician Newton, puts a question to him. He says, what would be the curve produced in a satellite if there were a force that diminished according to the square of the distance between two bodies? Without hesitation, Newton immediately answers an ellipse, the elliptical orbits of all the heavenly bodies and of the moon, as Kepler had argued in his laws of planetary motion. Halley is stunned. But how do you know that? And Newton said, oh, I worked it out some 20 years ago or so, but it was a bit off. It didn't correspond to the actual center of the work. Where are those papers? Halley asks. Newton begins rummaging through his drawers for them. As one historian of science famously put it, all of Europe was looking for a law of gravitation, and Isaac Newton had lost it. Newton finds it, Halley reads it, and Halley immediately sees the error of calculation as to the exact center of the Earth, and Halley understands that with the geography of the Earth corrected, the whole solar system falls into place. Kepler's laws of planetary motion are confirmed, and Newton has the mathematical proof of the nature and system and forces of the world. At Halley's urging and at Halley's private expense, Newton works on his discovery. He integrates it into his general system of the laws of motion, and Newton publishes it in Latin in 1687, the Philosophiae Naturalis Principia Mathematica, or the title is wonderful, The Mathematical Principles of Natural Philosophy, or as it simply would come to be known, the Principia. It took him 18 months to write, and it changed a culture and a culture's way of understanding the world and a culture's sense of the relationship of the human mind to nature. Thank you.